Okay, fourth changes. Should we make a new heading for this? Le Chatelier's principle. Luckily, you are not going to be tested on the French spelling. And that's a bit of a mouthful. Americans who can't pronounce French say Le Chatelier's principle. But if you are French, you would say it in a ridiculous French accent, Le Chatelier. Le Chatelier. Okay, but we don't have to pronounce it on an exam. We want an abbreviation. I would pretty much guarantee any marker would know LCP is short for Le Chatelier's principle. I will make a small adjustment to this definition. It's easy on your page. It's got to be an equilibrium system. So you've got to be talking about system is at equilibrium. Is subjected to an external change, the system will, can you add two words? Try to. There are some situations where it might want to adjust, but it finds itself unable to. Sorry guys, I hope the sound's been all right. Didn't have the microphone on. I'll say that again. I would prefer this statement to read, if a system at equilibrium, just to put that emphasis on the equilibrium, you can't use LCP unless the system is at equilibrium and you're subjecting it to an external change, you do something to change that. I call it the naughty boy principle. And you will know exactly what I mean if you've got a cheeky younger brother. Whatever you tell him to do, he does the exact opposite. Le Chatelier's principle in a nutshell. It tries to oppose your change. What do I mean by that? You heat it up, it'll try to cool itself down. You squish the volume, well, it probably can't oppose that. You've squished the volume, but you've increased the pressure. It'll try to decrease the pressure. Okay, what else might you do? You add a bit of extra. It'll try to take it away. You take something away. It'll try to put it back. Got the idea? It'll oppose the change. Let's look at some lovely examples of Le Chatelier's principle. All right, I'm going to let you work through the veggie sort of stuff and just get down to what does it look like graphically, because that's really how you understand it. You can fill in that table, I think, fairly easily. So I'm not going to waste time on that. I'm not going to waste time on 18 and 19. I want to go straight to question 20. Oh, sorry, there was something else I wanted to change. Go back to this page. So on that page, I wanted to delete something. Here it is. On this page, can you find this line? This second dot point, volume changes at constant pressure. No, 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 no. Volume changes at constant temperature. Could you run through? Because that's how, by changing the volume of a gas system, if you change the volume, the pressure will change. So it's definitely not at constant pressure. Sorry, that's a typo in your notes. Please delete constant pressure. So that line now reads, volume changes at constant temperature. First line was concentration changes at constant temperature and volume. And the third dot point was temperature changes. Let's cover all of them and let's do it graphically because that's the most fun way and the most obvious way to test it. Now, a couple of things. K is a constant, but it does change with temperature. Annoying. We'll need to know how. We will find out how. So K will not remain unchanged if there is a temperature change. So we will assume that K stays constant. It is a constant after all, as long as the temperature is constant. Let's rephrase that, it's important. K is constant if T is constant. But, important but, CF can temporarily change. And that just means it's out of equilibrium. We'll look at how that affects some numbers. Let's go. You take 3 deep breaths. We've been going for a long time now. We've got half an hour to go. Do you reckon you can handle another half hour? This is the coolest stuff though, Le Chatelier's principle. Let's enjoy. Okay, easiest one is question 20. So skip through that veggie stuff, go straight to the most obvious and easiest application of Le Chatelier's principle is adding or removing a reactant or a product. So there's at least 4 things under the same heading. Add one reactant, remove one reactant. Add one product, remove one product. Don't try and remove everything. That's not going to work. You're just making a small change to the system. So 4 changes for the price of 1. Add a reactant, remove a reactant. Add a product, remove a product. Naughty boy has got an easy way to fight that change. Let's see how. Let's look at it graphically. Read the notes. I'm not going to read through them. Let's look at question 20 from a graphical point of view. They've given you the LCP argument. I want to look at this. Now, what did we do? We've introduced the following changes. So for question 20, I'm going to say, right, what have we done? A, oxygen is removed. How much oxygen? It doesn't say. So graphically, we're going to have to make up a number. All right, let's put some numbers on the axes just so that they make sense. Let's go 2, 4, 6, 8, 10, 12. So my SO2 is starting at 12. My O2 is starting at 9. And my SO3 is starting at 5 on those axes. Now, the question said, remove some oxygen. How much? Don't know. I'm going to say remove 2 mole per litre. Let's have this in mole per litre of oxygen. Maybe if it's 1 litre container, remove 2 mole. Because I've got a concentration, and it's usually concentration you're talking about, but it could just as easily have been mole on that axis, but it's labelled concentration. So I'm going to remove 2 mole from every litre of my container. If it's a 1 litre container, I've removed 2 mole. So straight away, that goes down 2. Take it down 2. Do that now. The O2 has gone down by 2. So it's now down to 7. Le Chatelier's principle says the system will try to partially oppose the change. Partially oppose. It can never completely oppose the change. Now, that means the system will favour the reaction that puts oxygen back into the mixture. That's the back reaction. If you look at the reaction on your page, the back reaction will give you more oxygen. So that's what the system will do. Now, never say Le Chatelier's principle will put the oxygen back. No, Le Chatelier's principle is just a principle. It predicts that the system will put the oxygen back, but partially oppose. Now, was that in the wording? Let's go back to that wording again. That's really important. Read through that wording again. Partially. So in fact, I'm going to come back to this definition again and really put the emphasis. It's got to be at equilibrium. Subjected to change. The system will try to adjust itself to partially oppose the effect of the change. So don't forget that partially oppose, right? Screen back to the question. Should have done that while I was there. And let's look at this graph. Graphically, it started at 9. You animal, took out 2. It's going to try to put that 2 back, but it can't put it all back. It can't go back to where it came from, to use that SBS racist language. All right? The partial opposition of a change, the system will try to replace the oxygen you've removed, but it can't completely replace it. So I'm going to say it replaces one of them. I don't know how much, but it is going to go up, and it's going to come to a new equilibrium. I'll stop it. I wish it wouldn't do that. And I'm going to say, okay, it's going to come back to equilibrium here. New equilibrium. Old equilibrium. Change. Give you a chance to get that on your graph. So I've got it going back up to 8. But I've made that up. I don't know that it's going to be 8. So I'm going to put 8 question mark. So nobody's going to talk about, okay, you've got that 8 wrong. But having chosen 8, I know it can't go back to 9, but it will go up from 7. How much? I don't know. But it will be up, but it won't be as far as 9. It can't completely oppose the change. But having decided on 8, that means 1 extra oxygen has been produced in the back reaction. From your point of view, that's the back reaction. And looking at the stoichiometry, you can't make 1 extra O2 without making 2 extra SO2s. You get 2 SO2s, so the SO2 has to go up by 2, and it will reach the new equilibrium there, and it will go up. Now, having guessed 8, I'm now going to say, forget that. I've had to have somewhere on the graph. I'm going to call that what I don't know, and I'm going to call it's going to go up by X mole per litre. Don't know what X is, but I know it won't be as far as back as where it came from. But get the stoichiometry right. If that's gone up by X, then this must have gone up by 2X. So my strong advice is you show your marker that you've thought about the stoichiometry. Whatever the O2 goes up by, the SO2 must go up by twice as much. And the SO3 must go down by twice as much. So it's going to go down to the new equilibrium to here, because that is the 2X down. And it will do it in this shape, initially quickly, and then adjusting to equilibrium. Initially fairly quickly, oops, very hard to do this freehand on there. So strong advice, this, stoichiometry. Certainly on a SAC test, that will be looked at by your teacher. It's sometimes checked on a VCAA exam. But if you don't put X's and 2X's, you're forcing your marker to get out a ruler and see if you've thought about the stoichiometry. You can save the marker the trouble if you put X's and 2X's to show that you've thought about the stoichiometry. Now, to anticipate the last couple of pages, which we won't get to, I'm going to say, well, what if we did a rate time graph? For this change. Not very common on exams, but occasionally. Definitely common on mean teachers. Well, I don't know what the rates were. It was at equilibrium, but I do know that if it was at equilibrium, then my rate forward and my, oh, I better do it in different colour, hadn't I? Must have been the same. It was at equilibrium. Whoops. Rate back. Rate forward equals rate back because it was at equilibrium. Now picture, by collision theory, What would you expect that to happen when we do our change? Here it's at equilibrium. Change. Change was remove O2. Well, collision theory says if you've taken O2, the forward direction must get slower. Okay, rate forward in red must get slower because there's less frequent collisions between the SO2 and the O2 because there's less O2 present. But what about the rate of the back reaction? Have you taken away any SO3 instantly? No, you haven't. Have you added any SO3 instantly? No, you haven't. All you did was remove O2. So I don't think the rate at which the SO3s are meeting each other is instantly changed. So I reckon the rate of the back reaction is the same. Now that's why it's out of equilibrium, because the rates are no longer the same. To get to equilibrium, they will have to favour the back reaction. And if you favour the back reaction, you're going to get more reactants. And if you get more reactants, they will meet more frequently. So the rate of the forward reaction must increase. Okay, go back to red. Go back to red. My rate of the forward reaction will have to increase. And because I'm favouring the back reaction, there's going to be less SO3. And if there's less SO3, they will collide less frequently. So the rate of the back reaction must decrease. Okay, in blue, it will decrease. Where will it decrease to? It'll decrease until it meets the rate of the forward reaction, and then it's back at equilibrium when the rates are equal again. Now, isn't that cool? And collision theory allows you to predict that, but think it through very carefully. This is the easiest situation. You might want to practice the three other changes. What if you'd added some O2? What would the graph look like? What if you'd removed some SO2? What if you'd removed some SO3? You see there's a few other changes you could do, and they would have exactly the same logic, but the graphs would be different. Okay, I'm going to move on from that. That is the easiest application of Le Chatelier's principle, adding or removing a reactant or product.